This lecture is going to give us our introduction into the topic of thermochemistry, which is chapter 9 of the OpenStax textbook. And a couple things we want to sort of be able to answer and think about throughout this chapter are the questions on this slide. What is energy? How does burning coal or burning fuel enable us to move a car? And along the similar lines, when we eat food, where does that energy come from? How do we get food from eating, and where is that actually stored? And so a couple definitions we're going to have to go through to start this chapter. We can start off with the energy. One of the simplest definitions of energy is the capacity to supply heat or to do work. One of the key principles of energy is what's known as the law of conservation of energy. Just like the law of conservation of mass we talked about earlier in the semester, energy cannot be created nor destroyed. So all the energy of the universe there ever was is all the energy of the universe there ever will be. So we can't make energy out of something. But what we can do is convert between different types of energy. And that's most of the time what we're talking about. How can we change the type of energy into something useful? One of the earliest forms of this is taking some fuel source like coal and burning it, and taking the heat that gets produced from burning coal and using it to move something, like a train. And this really is the foundation of a field of science called thermodynamics. So heat, thermodynamics, movement. How do you take heat energy and convert it into movement energy? All right. And a couple more definitions for us. So when we think about energy, we can think about a couple different types of energy. And very broadly, we can think about what's known as potential versus kinetic energy. And so potential energy is the energy due to position or composition, and kinetic energy is the energy due to movement. And so an example of this is a ball up on a hill. So if we have some ball up on a hill and then ball B is down at the bottom of the hill, ball A is being held in place. This has a higher potential energy. So when they're not moving, they both have zero kinetic energy. But ball A has a higher potential energy because of its position. If we release it due to gravity, it's going to pull down and it's going to knock ball B. And what would happen? It would knock ball B and push ball B up this hill. So what we're really doing is transferring energy. Ball A has a high potential energy. It gets converted to kinetic energy, and then it transfers its kinetic energy to ball B, which pushes it on. In the process, not 100% of the energy is transferred to ball B. We know some of it is lost through friction as heat. Now, that's a very physicsy example. We could look at a little bit more of a chemical example and think about, well, where does the energy come from in our bodies? When we eat food, where do we get that energy from? And we can think about this in a simple chemical reaction where this CHO, just think about this as a food molecule, right? So most food is made of carbon, hydrogen, and oxygen. And so we have some number of carbon, hydrogens, and oxygens plus O2. And eventually that food ends up as water and carbon dioxide. And the other big product of this reaction is energy. So what's actually taking place here is we have our energy diagram. We have our fuel source, CHO, at some arbitrary energy level. And as we start to break this molecule down, as we metabolize it in our body, remember, breaking bonds always, always, always takes energy. So our body needs to put in energy to break bonds, to separate the carbon, hydrogen, and oxygen from each other. But what is also taking place is after we're breaking those bonds, we are forming the bonds of the products. And it's this formation of bonds that releases energy, right? So we're getting energy back from formation of bonds. We had to put in energy to break bonds. And it's this difference in energy, which is the energy available for us to do work. It's the energy for our bodies to harness to do something with. And this is, again, an example of conversion of potential energy to kinetic energy. In chemistry, when we think about potential energy, It's the energy within bonds. So the chemical bonds are what are storing our energy, and it's the formation of chemical bonds that releases energy. So we often refer to internal energy, capital E, as the sum of all kinetic and potential energies of an object. So therefore, the delta E, remember delta just means change, is the change of internal energy. And we always define delta as the final minus the initial state. So it's the final energy state minus the initial energy state. So if we think about a chemical reaction now, we can think about the chemical reaction of hydrogen gas reacting with oxygen gas. So hydrogen gas reacting with oxygen gas to form water, there's your water molecules, and releasing energy. So what we see here on an energy diagram is the reactants are starting at a higher energy than our products. So when H2 and O2 combine to form water, they go to a lower energy state, and this is the amount of energy that is released. We release this energy, right? So here what we're seeing is the products have a lower energy, so energy is released. And one of the things we might think back to is, well, we said all energy was conserved, right? The law of conservation of energy. So where did this energy come from? If energy is released, how come this doesn't break our law of conservation of energy? And the answer is we have to think about everything that's going on. And when we think about this, we can think about defining the universe as being made up of two parts, the system and the surroundings. And this is really key. The system is really the chemical reaction. So in this case, the system is here, all of the molecules that are taking place in our chemical reaction. And the surroundings are everything else. And so when we think about this, when we talked about the law of conservation of energy, it's really delta E of the universe has to be equal to 0. But now we can see delta E of the universe is made of two parts, the change in energy of our system and the change of energy of our surroundings. So when this reaction takes place, what we're seeing is the molecules are coming together and they are releasing energy, and that energy is going into the surroundings, right? So delta E of the system is equal in magnitude and opposite in direction of delta E of the surroundings. Energy leaves the chemical reaction and goes into the surroundings around it. Okay. Now, this reaction that we just looked at is actually what's used on various rockets, including the Delta IV rocket, which is a hydrogen-fueled engine. So again, take hydrogen gas, mix it with oxygen, provide a spark, that explodes, produces a ton of energy, and forms water in the process. Right? That's the basis of hydrogen fuel. And the goal of all of this is when we have our energy, this energy that gets spit out of the chemical reaction, that's what we want to harness. And that energy, we can think of having two forms, work and heat. And the idea of all of this is to try and say delta E is equal to heat, which gets a Q, plus work, which gets a W. And what we want to do is maximize work and minimize heat. We want to make a chemical reaction and harness the energy that gets the most work. The work is what's going to move an object and minimize the amount of heat that is produced. So a little bit more about heat and work. I know it's a little confusing, but heat gets the symbol Q. All right, lowercase q for heat. It's the amount of energy transferred from a warmer place to a cooler place. This is thermal energy, so it's undirected. So a heat source radiates heat in all directions. And let's not confuse it with temperature, right? Temperature is a measurement of average kinetic energy, right? So we can use this to sort of monitor heat flow, but it is not itself heat. Work, lowercase w, this is directed energy. So we can move an object from one place to another. And again, the goal of thermodynamics is to minimize heat and maximize work. So we can go back to the first law of thermodynamics, which is an equation we already showed. Delta E equals Q plus W. Right, so the energy of the universe is constant. So if we perform a chemical reaction and we have a change in energy, the total sum of energy has to be equal to all the heat produced or absorbed and all the work produced or absorbed. And one of the things that's really important for us to understand is the sign of energy values. When we think about a chemical reaction, if we think about, here's our reaction flask, some chemical reaction taking place in a flask. We're going to put it in a box for a second. When we think about this, when we talk about energy leaving the system, energy released by the system. So if a chemical reaction produces energy, the energy values are always negative. And if Q is negative, that means heat is being released, and we call that an exothermic reaction, one that is producing heat. If our reaction does work, work is negative, then work is done by the reaction, and we say it's done by the system. On the other hand, if our reaction is absorbing energy, a reaction can absorb heat, in which case Q is positive. We call it an endothermic reaction. And if work is greater than 0, we say work is done on the system. All right, so a little bit of nomenclature we need to be aware of. Now, we've talked about the system and the surroundings, so it's important to sort of identify a couple different types of system. Remember, the system is what we're studying, and the surroundings are everything else. So very broadly, we can define 3 types of systems. We have an open system, and this is just when matter and energy can be exchanged with the surroundings. We have a closed system, in which this can exchange energy but not matter. And we have an isolated system, in which neither matter nor energy can be exchanged with the surroundings. So an example to sort of illustrate this is a fish tank. So if you imagine your fish tank, and the contents of the fish tank are the system, and everything outside the fish tank is the surroundings. So an open system would be a fish tank with its lid off. So a fish is free to jump out. You can feed the fish, so we can put matter in or out of the fish tank. You can heat up the water in the fish tank, so you can provide energy to the fish tank, so that would be an open system. In a closed system, we'd have a lid on the fish tank. In this case, matter cannot go in or out, so you can't feed the fish, and the fish can't escape. But you can still put it under a heat lamp and transfer heat in the system, or heat can leave the system. In an isolated system, you can imagine taking your closed system and insulate this really well. And at that point, heat can't get in, heat can't get out, matter can't get in, matter can't get out. So that would be an example of an isolated system. All right. So again, how does a chemical reaction do work? So let's talk about this quickly, and just this idea of where do we get energy from and how do we get work out of it? So if we consider the example of your car, the combustion of octane. So this is an equation showing taking octane, C8H18, in the presence of O2, produces carbon dioxide, water, and energy. This is what takes place in your car, and this is the energy that moves your car. So how does that actually work? Well, when your engine is running and you're burning gasoline, right? So the delta E of this, so this energy is delta E, is going to heat plus work, right? So we know our engine gets hot, so actually most of the energy goes to heat, and a small portion of it goes to work. And that work moves your car. So how does that happen? What's going on here? And this is in generally how your car engine works if you have a fuel burning car. You have a piston that can go up and down, and you pump in gasoline, gas, and oxygen gas. So in this tiny area, you have oxygen molecules and gasoline molecules, all floating around right? And what happens is you have a small space, you provide a spark from your spark plug, right? And that produces this chemical reaction to take place. Now, what happens when this takes place is we have some gas molecules here, and in fact, we can count them and say we have 27 gas molecules here. When this reaction takes place, we're gaining gas molecules, right? Because suddenly we have 16 plus 18, right? So now we have more gas molecules on the product side than we did on the reactant side. And so more gas molecules take up more space. And so when they take up more space, we have an increased pressure. It's actually going to push your piston down. It's the production of more gas molecules that pushes the piston down. And this movement of the piston, going from this location to this location, is actually what drives your car. After that takes place, this gets pumped out of your cylinder, the piston comes back, we pump in more gasoline and oxygen, and the process repeats itself. So with heat again is the transfer of thermal energy between two bodies at different temperatures. And one of the important things to think about with heat is that if we have something that's hot and we have something that's cold and we bring them in contact with each other, the hot thing is always going to transfer energy to the cold thing, right? Until they are at the same temperature. So in the winter, if you leave your door open, your heat is all going to escape the house and go outside in an attempt to warm up the outside to the same temperature. Quickly, we'll just discuss energy units real quick. One of the most common units of energy that you may be familiar with is the calorie, abbreviated lowercase cal. This is the amount of energy required to raise 1 gram of water by 1 degree Celsius. Okay, so that's the formal definition of calorie. Now, this is a bit annoying, but it's important to know the calorie that you see on a nutrition label. So if you want to figure out how many calories you're eating in a day, is actually calorie with a capital C, which is actually a kilocalorie, right? So why do they use that? I don't know. It's annoying. But 1 capital C calorie is equal to 1,000 lowercase c calories. In chemistry, in physics, what we'd use more often than calorie is the joule. So joule gets a capital J, and 4.18 joules is equal to 1 calorie. To give you a little idea of what a joule is, if you dropped an apple 1 meter onto your head, the force that you felt on your head is approximately 1 joule. Heat capacity and specific heat, just a couple more definitions, and then we'll wrap up this lecture. The heat capacity, capital C, is a quantity of heat that a body absorbs or releases when a temperature change of 1 degree Celsius or Kelvin happens. This is a quantity of a substance, and we can think about this as being capital C equals Q over T. So again, what does this mean? It means how much energy, Q, does it take to change the temperature of a substance? And typically we do it by 1 degree. So how much heat do we have to put in to raise the temperature of a substance by 1 degree Celsius? The specific heat capacity, often shown as a lowercase c, is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree, right? So the difference here between the two is the heat capacity could be for an object of any size, and the specific heat capacity is specific to 1 gram of a certain substance. And so it's the same sort of equation, except now there's a mass on the bottom for 1 gram. Now we can look these up. So your textbook has lists of substances, elements, and their specific heat. And again, the specific heat is how much energy it takes to change the temperature of 1 gram of a substance 1 degree. And I just want to point something out to everyone. We can look at something like water. Liquid water has a specific heat of 4.184. That's the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. And just compare that with something like maybe aluminum. And notice the difference in that specific heat, 4.184 and 0.897. So aluminum has a very low specific heat. Now, what does that mean? Well, if you bake something in your oven's very hot, you go to pull it out, you don't want to touch the thing you're cooking, but if it's on a piece of aluminum foil, you can usually reach in the oven and touch that aluminum foil because of the low specific heat. Another way of looking at this is aluminum is not going to absorb much heat. Water is going to absorb a lot. This is one of the reasons why we have life on this planet, is water can maintain heat for a long time, whereas something aluminum is not going to be able to absorb any heat on our planet. So that gives you the basics to start out thinking about Chapter 9. We'll go into more details in the next lectures. Thank you.